Hello everyone, I'm Jinyu from Peking University, and today I will talk about WiPhone. Smartphone-based respiration monitoring use ambient reflected Wi-Fi signals. Accurate monitoring of human respiration plays a crucial role in a wide range of applications in healthcare, such as sleep apnea detection and sleep stage recognition. Recently, we have seen lots of different approaches for respiration monitoring, such as pulse oximeter, camera, and CW reader. Compared with these approaches, Wi-Fi is more appealing. We use off-the-shelf smartphone and community Wi-Fi router as a pair of transceivers, aiming to provide robust respiration monitoring in non-line of sight setting. However, designing an effective respiration monitoring system based on smartphone faces several technical challenges. First, SIGCHI signal extract from smartphone present a relatively poor quality. Second, it is difficult to guarantee the directly reflected signal path via human chest in a typical home setting. In this work, we aim to robustly monitor human respiration in non-line of sight setting. We first conduct our experiments in a typical line of sight scenario. We can observe a clear sine wave that matches the ground truth of subject's respiration when we use mini PC equipped with an Intel 5300 Wi-Fi card as transceiver pairs. However, the SIGCHI readings obtained by smartphone are noisy and scattered across the multiple values. We adopt dBscan to separate the respiration modulated SIGCHI signal from the noisy raw SIGCHI waveform. We randomly select 3 out of all subcarriers. We can observe that the SIGCHI amplitude in each of the subcarriers are scattered across the multiple values, and the resulting SIGCHI symbols represent a clear respiration patterns for different subcarriers. Respiration sensing using smartphone can be tricky because smartphone is usually carried around by user, while a Wi-Fi router is usually placed at a fixed location. In many scenarios, the line of sight between Wi-Fi router and smartphone may be blocked by human body, wall, and furniture in home environment. In this case, the directly reflected signal path used in existing work does not exist. We exploit ambient reflected SIGCHI signals in non-line of sight setting to qualify the relationship between SIGCHI signals reflected from the environment and the subject's chest displacement. As the change of propagation length dit for each RS path is caused by chest displacement, without loss of generality, we assume dit is of the arithmetic propagations, while ut represents the chest displacements caused by respiration. The formula can be calculated according to the summation forms of geometric propagations. We therefore use an amplitude only for respiration sensing. Obviously, chest displacement caused by respiration is far more less than the wavelength of Wi-Fi signal. Thus, the peaks or valleys of all trigonometric functions are all related to breathing in and out. We conduct comprehensive experiments in a real residential apartment with an area of 126 square meters, which consists of 2 bedrooms, 1 living room, 1 study room, and 1 bathroom. Asus RTAC 86U Wi-Fi router is used as transmitter and Google Nexus 5 as a receiver. We focus on the scenarios where Wi-Fi router and smartphone are located in different rooms with a wall in between, as shown in floor plan of apartment where a red circle and green triangle represent router and smartphone representatively. The mean error of respiration rate for each of the setups is less than 0.5 breaths per minute, demonstrating that the respiration sensing capability of WiPhone is lower. We further evaluated the sensing ability of WiPhone through multiple walls and discovered the sensing range distance in a home setting. We set up experiments with a range of direct distance between router and smartphone up to 10 meters through multiple walls in between. A clear respiration pattern can still be observed for both through-wall scenarios. At last, we conducted the experiment based on symptoms of abnormal respiration. Now I will summarize our work. First, we proposed a Daqing-based preprocessing method to extract useful CSI amplitude pattern for effective respiration monitoring. Second, we established the relationship between human movement and ambient reflection signal. We design and implement WiPhone on off-the-shelf smartphone. Extensive experiments show that WiPhone achieves a represent rate error of 0.31 breaths per minute on average in a range of non-line of sight settings. That's all. Thanks for your attention.